All right, guys, welcome to IM1 Functions Day 3. We are talking about slope a little bit more and also associating it with what's called the rate of change. So, rate of change is just another word or phrase for slope. So, actually, what we did in class here is we began by kind of looking around the classroom, and you can do this wherever you're at, and just look and see where lines exist around you. Uh, there may be some lights up above you that are linear. There may be like a doorway, right? It looks like it may have two vertical lines and a couple horizontal lines that are rectangular. See if you can look around and see something that has an increasing slope from left to right or a decreasing slope from left to right. It would look like it would be going up if it was increasing, down from left to right if it was decreasing. So what we did in class was we just basically made a list, and we said there are really no wrong answers here. Linear functions exist all around us. And then we asked ourselves, how could we determine the slopes of these functions? What tools would be useful? Some students said, well, there's the equation y2 minus y1 divided by x2 minus x1. And this was drawing on some prior knowledge, some previous knowledge here of the slope formula. They'd maybe seen this before, but when you're talking about y2, y1, x2, x1, you need coordinates on a graph to be able to calculate the slope there. So when we're looking around our surroundings, coordinate pairs don't really exist. You could designate something maybe as the origin, right? And then determine a rise or a run from there. We'll look at a couple examples, but really when you're working with y2 minus y1 over x2 minus x1, this right here will only be used when you have points on a coordinate plane, right? So what you'd actually want to think about is, well, what could we do in the real world? Like if we're going to measure something in the real world here, maybe you remember slope as rise over run. Now, when you consider rise over run, now look at that line again that you identified in your surroundings, and see if you can determine a beginning point and an end point. And if you were to measure the rise and the run from that beginning point to that end point, what tool would be useful? Maybe you would use a yardstick, maybe a tape measure. And what you could measure here is the actual rise, the vertical change in inches, and then the horizontal change from a point in space over to the end point, right? So that would be your rise and your run. So we'll get a little more into that. I actually have an example that will help that make a little more sense. But then what we considered is, can you come up with an equation that models slope? So what we did again was we looked at this vertical change over this horizontal change. Okay, so if you consider points on a graph, if you're going to actually use an equation, right? If we're talking about this line segment here with a beginning point and an end point, there would be values here, right? Values for y. So let's just say this has a y value of y2. Let me clean that up a little bit. It's a little messy. Let's say that has a y value of y2, and this has a y value of y1. Let's see here. Let's be a little more specific here. So this point right here would have a value of x2. So how do we get to this point from the origin? We would go right x2 and up y2. So that's going to give us a coordinate pair of x2, y2, right? And if we wanted to get down to this point, we would go left x1 and down y1. So we're going to call this point x1, y1. Okay. Now, when I'm talking about horizontal change and vertical change, let's use yellow here. If we want to get from x1, y1 to x2, y2, we're going to rise a certain amount, right? Some certain amount here we're going to rise. And then we're going to run a horizontal amount, right? So when we're developing this y2 minus y1 over x2 minus x1 formula, what I want you to think about is this right here, change. That little triangle there means change. We're looking at the change in the y's here. So when we're going from this point up to this point, what is that length? What is that distance? And you can get that by doing the value of y2, whatever it is, subtracted by y1, and that will give you your vertical rise. Same thing goes for our x's. Okay, so what is this run right here? This horizontal change, right? And we're going to call this the change in x. Well, that right there can be modeled by x2 minus x1. If you take this value of x2 and subtract x1, that's going to leave you with this horizontal change. So when you do your rise over your run here, y2 minus y1 over x2 minus x1, that's going to give you the slope of this line segment. Now what we just created there is what's called a slope triangle, and that would be increasing. So you always read a graph from left to right, and this thing is moving in the upward direction from left to right. So this would be considered increasing. Okay, this guy is increasing, linear. All right, so that is how you would determine and make sense of an equation. But let's see what we got today. So connect the slope of a line to average rate of change of a function. We've got horizontal change and vertical change. I mean, we already just talked about that, huh? We talked about increasing. We'll talk about what decreasing and constant are as well. And we've already referred to rate of change, so we're off to a pretty good start here. So let's see what number one has for us. So today, what we did in class is we looked around the river building, and we were looking for where, again, slope exists around us. So let me show you the example I came up with here in class. So I shared this with everybody in class, and then they had to go out and do it 3 times on their own. Okay, but for each linear function, for each of the 3 linear functions that they found in the river building, they first had to describe where in river they were and why it's an example of a linear function. And what I said is, I'm in river 306, and I'm measuring the slope of a student chair. This is an example of a linear function because the slope of the chair leg is continuous, meaning the common difference would be the same. So what I was finding the slope of was that back left leg there, right? It looks like it has an increasing slope. Okay, so it's going from that point there, beginning point, to that point right there. That's going to be its end point. It's going to be increasing, right? So determine the slope that represents this linear function. The rise was 17 and the run was 7. Now, how did I do that? From this point here, I dropped the tape measure directly down to the desk here. Okay, that gave me a rise of 17 inches. Okay, and I made a mark right on the desk, right about there where my cursor is. I reset the tape measure, and I measured the horizontal change from that mark. Okay, so basically what I did was I measured a vertical change and then a horizontal change. And that's all slope is. It's a vertical change divided by a horizontal change. So my slope is 17 over 7. Now I have to consider, is this positive or negative? And because it's going up from left to right, it is a positive slope. So 17 over 7. C asks you to describe how you determine the slope. And I explained that I used a tape measure, and I measured directly down to get the vertical change, made a mark, and then measured the horizontal change. Now D, this is my attempt at kind of tricking some people in class. Write a linear function for this example. What do you think that 29 is, and where do you think that 29 comes from? And actually, one person in the 2 classes that we had was able to figure it out, and it's that the student desktop was 29 inches off the ground. So when you're looking at this, this represents where my cursor is, the bottom left part of the leg of the chair, and it is 29 inches off the ground, hence the y-intercept of 29. Now, I was kind of getting fancy there. If you have something that is starting from the ground, then its y-intercept would be down here at the origin, and it would just be, for example, 17 over 7x, and that would be it, plus 0, right? You don't need to put the plus 0. But because mine was elevated, it was not sitting on the ground, considered the x-axis, then I had a y-intercept at 0.29. So try this in class, or not in class, sorry. Try this wherever you're at if you're not able to be in class today, and see if you can do this a few times around your house. So this is what we did in class. We did it 3 times. Now down here, this basically is just explaining again what we just talked about up here with this y2 minus y1 over x2 minus x1. What we were talking about, can you come up with an equation that models the slope? This is breaking it down just in a bit of a different way, so feel free to read through it if you'd like. instead of using y2 and y1 and x2 and x1, they're using t and f of t and s and f of s, but it's basically just the same thing. Once again, I think we called this up there. Here, let me just, for consistencies. Up above, I think we called this x1, and that's x2. This would have been y2, and this would have been y1. Okay, so this point up here would be considered x1 and y1. And this point down here would be considered x2. Let's see, I made that mistake here because we're traveling right x2 and up y2. Sorry, this would be x2 and y2. So maybe you're out there correcting me at this point. Let me back up here and make that correction there. So this would be x2. Sorry about that. x2, y2. And then this guy down here would be x1, y1, right? Because how do you get to that point? You travel right x1 distance and up y1. So same thing goes. If we want the vertical change, we're just going to subtract this y value from that y value, and it's going to give us what's left over for our vertical change or our change in y. And then this horizontal distance is going to be represented by our x2 minus our x1, and that's going to give us our change in x. Okay, and again, slope is equal to the change in y over the change in x, okay, which is just rise over run. All right. So down here, in example 2, we wanted to consider the slope of this graph. What would it be? So you could choose any 2 points that you want. You could choose these first 2 points here and here. You could choose this point and that point. You could choose this point and that point. You could choose this point and that point. It doesn't matter what 2 points you choose. No matter what, the slope should always be the same. So let's see. Let's choose this one and that one. Why not? Okay, so this ordered pair right here would be 4, 10. And this ordered pair right here would be 2, 6. And we want to calculate the slope of that graph. So let's just do it between those 2 points. First off, now if we call this x1, y1, and this x2, y2, our formula would look something like this. It's y2 minus y1 over x2 minus x1, and then we just plug in accordingly, right? Make sure that they correspond. So y2 was 10 minus y1 was 6 over, and when I say correspond, you have to do the x2 that goes with y2. So in this case, it's 4 minus 2. So what that gives us is 4 over 2. So that gives us a slope that is equal to 2 when we reduce it down. Now, some of you out there may remember rise over run. So if we want to use rise over run from one point to the next, this rise here would not be, careful, it's not 1. I know it's 1 box, but this scale goes by 2s. So this would be a rise of 2, and this would be a run from this point to this point of 1. So again, it checks out. It's 2, rise 2, run 1. The slope is still 2 over 1. What is the linear function of this graph? Well, at this point, hopefully you're getting comfortable with determining sequences, and you know the zeroth term has relevance. The zeroth term is the y-intercept. So if the value of our first term is 4, okay, that's just an ordered pair, 1, 4. The value of our second term is 6. Once again, that's an ordered pair on our graph. And the value of the third term is 8. Once again, just another ordered pair on our graph right here. We could actually work backwards. It looks like it's adding 2 each time. So if we want to work backwards, our zeroth term would be 2. So if we want to write a linear function in the form of f of x is equal to mx plus b, then that would be, f of x is equal to our common difference or our slope of 2x, or 2 over 1x, just 2x works, plus our zeroth term or our y-intercept of 2. And you can see that graphically as well here. If you were to backtrack to find the y-intercept, going up to right 1 would be the same thing as going down 2 and left 1, and that would give you right there at that y-intercept of 0, 2. If you were to find the rate of change between the points 1 and 4, did we already do that? Nope, we found it between 2 and 4. So let's find it between 1 and 4. So let's get the ordered pairs. So the points 1 and 4 means the point 1, 4. Okay. And the points 4, what is that, 10. So let's find the slope between those two. I would encourage you to pause it right now at this point and see if you can do that using the slope formula, y2 minus y1 over x2 minus x1, and then see if you can come up with what I came up with, okay? Pause it and give it a shot. So let's see here. If we do y2 minus y1 over x2 minus x1, we're going to get crazy here, and we're going to do this backwards and call this x2, y2. And you probably called that x1, y1, but it doesn't matter as long as they correspond. Let's go y2, 4 minus y1, 10. I'm just going to end up with a couple negatives here, but that's okay. x2, 1 minus x1, 4. That's going to give us negative 6 over, sorry about that, negative 6 over negative 3, which gives us a slope of 2. It still checks out. It's going to be the same. Lastly here, slopes can be described as increasing, decreasing, or constant. What do you think those terms mean? You'll want to do a little research here, but we, again, already kind of have referenced this throughout the lesson today. Increasing is going to go up from left to right, okay, up from left to right. Decreasing is going to be going down from left to right. And you'll notice that it has a negative slope. Okay, and we should say up here that this guy is going to have a positive slope. Okay. Positive slope. And then a constant slope. What we're talking about here is just this horizontal slope, something that doesn't have a slope, right? Whereas all lines have constant slope, right? The slope is not going to change if it's linear. I believe what we're talking about here, just to make sure that you guys are on the same page with us, is that zero slope makes a horizontal line. Okay, but we're going to talk more about that in a future lesson. Make sure you do self-assessment, make your corrections, watch the video, do the portfolio, all that good stuff. Test is coming up here pretty soon, and you should be in great shape. All right, guys.